And we got the general idea of what a limit was. And we've looked at some 0 over 0 limits. And today we're going to look at one-sided limits. So sometimes the limit as you come from the left side of a graph or of a point is different than if you come at a limit from the right side of a point. And some functions are too complicated to write all with just one equation, so they get written with multiple equations and are broken up into pieces. And because they're broken up into different parts or pieces, they're called piecewise functions. So here's an example. You've got a function f of x that has two different parts. One part is a line, 2x plus 1, and the other part is a parabola, which is x squared. And what this notation means, so usually you just have an equal sign in one equation, right? In a piecewise function, you have an equal sign and can have multiple equations, and each equation has its own domain. So 2x plus 1, if you graph that, that'd normally be a line with a y-intercept of 1 and a slope of 2. But now we only draw this part of it when x is bigger than 1. And the parabola, x squared, you know what a parabola looks like. Well, now we only draw part of the parabola when x is less than 1. And because there was an equal sign with the 2x plus 1, at the point 1, 3, we show that with a solid filled-in dot because it's part of the equation. But on the parabola, at the point 1, 1, we do an open circle because the value of 1 is not included in the equation. So we just graph something with two different pieces. This comes up like a real-life example. Sometimes you might have a credit card that gives you one benefit for the first $1,000 you spend, and then another benefit for the next $4,000, and then another benefit if you spend over $5,000. So each of those pieces would be a slightly different graph, and if they wanted to show it all together as one, they'd have to show it as a piecewise function. Here's just some, if you were wanting to graph this, just finding some points, you could make a table of values. But I think these are both graphs that you already know. So now we get to a new definition. What is a left-hand limit? And what does it look like? So a left-hand limit has a tiny little negative sign beside the number. So here we have limit as x goes to 1 from the left-hand side. So what does this mean? Is if you were on the left side of 1, here we'll just draw, there we go. There you are. Would you agree the happy face is on the left side of x equals 1? And as that happy face gets closer and closer and closer to 1, what does the y value get close to? The y value gets close to 1. If you're coming from the left-hand side, the happy face is approaching 1. We'll see that if you come from the right-hand side, it gets close to 3. So we would say that if it's coming from the left-hand side, then you're on the green graph, and your y value would be getting close to 1. The little plus sign is a right side limit. This little plus sign here means if you were coming from the right side, and getting closer and closer to 1, then your y values would be getting closer and closer to 3. But we say that the limit as x goes to 1 in this equation does not exist. Even though you can plug 1 into the equation, right? According to this equation, if you wanted to find out what it's equal to when x is 1, you would say, oh, I have to use the top equation. And when I plug in 1, I get 1 comma 3. And in all of our previous examples, if we wanted to find a limit and we could plug in a value, we could just plug in that value and find it. The difference here is this graph is not continuous at 1. You can't draw it without lifting your pencil. You have to pop your pencil up and start again as you shift from the green graph to the blue graph. And we say in order for a limit to exist, if you approach from the left side and you approach from the right side, it has to equal the same thing. I think in your homework there's some crazy, interesting, well, weird-looking graphs. I think there could be one like this. Let's say you got one piece of your graph, which I'll draw like this, and then it has okay. And it has a whole so here we have a graph that looks like a parabola with a hole in it, and where the hole is, there's just another point instead. So for this graph, does it make sense that the domain is everything? Every x value is allowed. Even though there's a hole, they've got an extra point here. Okay? So every x value is allowed. Would you agree that if you had to figure out what f of 1 is, you can see it from the graph? If you plug in 1, what's your y value? Well, where's 1? Oh, it's up here, right? F of 1 is 1. Okay? The limit as x gets close to 1 of this function is okay, negative 2. So when you plug in 1, the answer is 1. But if you get close to 1, you get closer and closer to negative 2. This is this idea. If I take my little happy face back down to this graph, the idea of a limit is if I come towards 1 from the right-hand side, that's where I'd get close to. If I would approach, whoa, get my happy face back there. If I approach from the left-hand side, that's where I get close to. And since I get close to negative 2, both from the left-hand side and the right-hand side, that's my limit. The limit is the value that it gets close to from both sides, even though you have a value that f of 1 is equal to 1. So a limit is not always just what you get when you plug it in. A limit is what the graph is getting close to, what it's approaching. And in this case, the limit as x is getting close to 1 would be equal to negative 2. So whenever this one, the normal limit, whenever you approach from left or right and it approaches a different number, then we say that limit doesn't exist. But if it approaches the same number from the left side and the right side, then the limit does exist. So this is how you would say it in fancy mathematical notation. If the limit from the left side doesn't equal the limit from the right side, then the limit does not exist. But if the limit from the left side equals the limit from the right side, some number L, then the actual limit is that same number. Even if we have what we had in that previous example, a separate point where it was equal to that. Okay, I'll get you to try this one. First of all, draw the graph. And then evaluate the limit. I'll put up the graph so you can see if you graphed it correctly. So I graphed the parabola part in green and the line part in blue. And notice that on both the green and the blue part, you would have the point 2, 4, but technically the 2, 4 would come from the blue graph because there would have been an open circle on the green graph at that same point. And if you think you have this one already, you can go on and try example 4. Questions? So we're going to use this line when x is bigger than 2. And if you've drawn this part of it, that would be where x is less than 2. And so what is the limit as x gets close to 2? The answer is 4. Why? Because if you come from the right side, which is on the blue graph, it's equal to 4. If you come from the left side, which is on the green graph, it's equal to 4. And since approaching 2 from the left and the right is the same number, we can say that the actual limit is equal to 4. Oops. If I was labeling some things on this graph, this hole would be at 2, 7, and this solid point right here would be at 2, 15. So are you starting to see how the pieces work with the domain? We're only taking this x cubed minus 1 graph when x is less than 2. So here's 1, 2. We're taking this part of it where all the x values are less than 2. And for the blue graph, we're only taking that when x is bigger than or equal to 2. So that would start at 2, 15 and include all the values to the right. For this one, if we wanted to find the limit as x goes to 2, it's not going to exist. Because if you come from the left side and the right side, you get different values. From the left, on the green one, it gets close to 7. From the right, you'd be on the blue graph, it gets close to 15. So we would say this limit does not exist because the two values are different. Boy, a different way of thinking about limits. What if you had a series of numbers like this? 0, 0.2, then 0.22, and then 0.2222, and 0.22222, and so on. Does it get closer and closer to a number, or does it just keep changing? What do you think it gets closer to? And 2/9 as a decimal is 0.2 repeating. Does it make sense? If you went on infinitely, you just keep getting more and more 2's. And so in this example, I'm not going to hit the purple things off on this one. Just looking at it, looking at the next 3 terms, well, you could put 0.2222 and 0.22222 and then 0.222222. Should have got money for some sort of pizza advertising at this moment. Anyways, it would keep going, and if you did this forever, it'd get closer and closer to 0.2 repeating. And 0.2 repeated as a fraction is 2/9. I was actually showing my grade 9s this today. Did you know how to change any repeating decimal to a fraction? Have you learned that? Do you know how to change 0.17 repeated to a fraction? No? Oh. It's really cool. 0.137 repeated would be, any guesses? Yeah. And that's pretty cool. And then you can figure out stuff like mental math. What's 2 11ths? 0.18 repeated. How did I do that? Made it to the same as 18 over 99. Pretty cool. Yeah, none of you have siblings in my grade 9 class because I was going to tell them to go impress their siblings and with their new mathematical abilities of repeated decimals. Okay. Oh. Okay, I'll just get a little bit off topic with thinking and brain stuff. Which number is bigger? 0.9 repeated or 1? Do you agree with them? They're equal? Or does that feel weird? Would your gut want you to say that 1 is bigger than 0.9 repeated? That's what you're, okay? But if the repeated sentence says, oh, this is 9 over 9, isn't that equal to 1? Now, using that pattern, sometimes people would argue, that's like a, I don't think that's true, okay? But it is true. 0.9 repeated is equal to 1. If you want to be really annoying to your science teachers from now on, every time you get an answer on a test that's 3, you would say, oh, I'm just going to write that as 2.9 repeated. But they'll probably mark you wrong, and then you'd have to argue with them that they're the same number. And then they probably won't like that and still mark you wrong. So I don't think it's worthwhile. But you could. Now, this pattern of just saying, oh, anything repeated is over 9, so it's 9 over 9, so it's 1, I find often students don't feel like that's a very convincing way of saying that 0.9 repeated is 1, because it seems like I'm kind of flexing it a little bit. So you could try to show 0.9 repeated is equal to 1. And technically, two numbers, if two numbers are different, there's always a number in between them because of how numbers are infinite. There is no number in between 0.9 repeated and 1. Hence, they must be the same. But another way to prove that 0.9 repeated is 1 is you could use a different fraction. Say I take 1/3. 1/3 is 0.3 repeated, right? And if I took another 1/3 and another 1/3, it's obvious if I add these together that this side is 1. 1/3 plus 1/3 plus 1/3 is 1. But if I took the decimals, what's really cool about adding 3's on infinitely is you never have to carry over the 1. They'll all just add up to 9's forever. So maybe that's a little bit more convincing of why 1 is equal to 0.9 repeated. But let's do it in algebra. Let's pretend x is 0.9 repeated. Goes on forever. Okay? Would you agree then that 10x's just would move the decimal place over 1 and make it 9.9 repeated forever? Now, if on this side I subtract x, then on this side I would need to subtract x, because what you do to one side you do to the other. And what's x equal to? It's equal to 0.9 repeated. So if I subtract x on this side, the algebra side, I'd have to subtract 0.9 repeated on this side. Now, 10x minus x is 9x. And 9.9 repeated minus 0.9 repeated is 9. And if I solve for x, what do I get? 1. But what did I start with? I started with 0.9 repeated. And they end up being the same. So there's sort of 3 different ways why 0.9 repeated is equal to 1. Sorry, got off topic there. Just a little bit. So a little bit of a review of some stuff. What does the word continuous mean? A function is continuous if the limit is equal to the value. Okay? So let's take just a parabola and imagine the point. This is x squared, which is a continuous function because we can draw it without lifting our pencil. And we take a point on that parabola, 2, 4. If you plug in 2 into x squared, you get 4. The limit as x gets close to 2 on x squared is saying if I come from the left side and I come from the right side, I'm getting close to 4. And because the limit is equal to 4 and the function is equal to 4, we know that it has to be continuous at that point. Do you remember the one that I showed you that was not continuous? Right at the bottom of this page, where I had a hole in the graph and it's another point. This function, the limit exists. The limit as x gets close to 1 is -2. But the value at 1 is 1. So we would say this graph is not continuous. The limit exists, the value exists, but they're not the same. And a lot, if you go on to study mathematics, pure mathematics at university, a lot of mathematical functions, it's really, really important that they're continuous. If they're continuous at a point, that allows us to do calculus. It allows us to do all sorts of manipulations. If a graph is discontinuous or broken, then mathematics feels awkward and things don't work like we'd like. So if something is continuous at a point A, that means that that value is defined. It's not a non-permissible value. Okay? The limit exists always. And that the limit is exactly the same as the value. So let's look at a piecewise function with 3 equations. It's -3 if x is less than -1. It's 2x if x is between -1 and 1. And it's equal to 3 if x is bigger than 1. I'll let you try to graph that first. And I color-coded mine. I made this section blue, the middle section green, the last section black. Do you remember the test to tell if something's a function or not? What did we call that? Right, if there's more than one y value at the same x value, and a very easy and quick way to test it is by using a vertical line. And it's called the vertical line test. So nice and easy, because I could take this, whoa, wait for it. I could take this vertical line, and if I go across, no matter where I am, I only hit the graph once. Even at these places where it switches over, one of them has an open circle, one of them has a filled-in circle. So that's very important because we call these piecewise functions. They still have to pass the rule, the vertical line test, that says they're functions. So here's our graph. And now we are to see if we can figure out the following limits. If possible. Some of them are left side limits, some of them are right side limits. And I'll put the answers up in a bit. Oh, I like the colors. I like the highlighters. Yes. Yeah, are you doing a table of values for each one separately? Yeah.
Okay.
Yeah, so if you were plugging in 0, it would be in this one, right? And 2 times 0 would be 0, 0. That's why my graph, it's a little bit drawn. It should go through 0, 0. Does that make sense? So that negative is the left side limit. The plus is the right side. So you're going to 1, but you're coming from the left side. So your 1 is here, so I'd be on the orange graph. I'd be on the orange graph approaching, and I would hit that point right there. Yeah, we might find it helpful on this graph to label that we have the point -1, -3. We have the hole at -1, -1. No, -2, sorry. We've got this hole at 1, 2. And on my black graph, I've got the point 1, 3. Those places where it changes from one graph to the other, those would be good ones to label. And then if you were approaching f of x at -1 from the left side, -1 from the left side, do you see that you would be on the blue graph? And if you got to -1 on the left side on the blue graph, you'd get close to -3. If you approached -1 from the right side, you would be on the green graph. And if I went to -1 from the right side, I would get close to -2. If I'm going to 1 from the left side, I'd be on the green graph. Then I'd be approaching +2. If I went from 1 from the right-hand side, I would be on the black graph. And I would approach 3. Where is f discontinuous? Well, I think you can just, like, common sense logic look at it and see there's a break in the graph at -1 and 1. So at x equals -1 and x equals 1, those are the places where it's discontinuous. The values of the limits tell us that as well, because they don't equal each other. There's a nice looking graph. So try these ones on your own. Again, I'll put up the answers in a bit. I'll come around and help. Discussed with people next to you what you got for the first 4. All right, which ones do you want to argue with? DNE does not exist. That is not some other fancy, didn't it? It's not a word. It's just an abbreviation that it does not exist. Yeah, so f of -4, that one I look at the graph, it's a hole. Okay? Limit as x goes to -4 from the left-hand side. I would be coming from this side towards -4. Am I getting close to a value? I'm getting close to 2. Okay? Here, okay, here we're going towards -4 from the right side. So I'm on the right side, I'm going towards -4. I'm getting closer to 2. Okay? And for the last one, what's the limit as you get close to -4? Whether you come from the left or the right, you're approaching 2. Even though there is a hole there and it doesn't exist. Tell me when you guys are ready for the next 4. You're ready. Ready? Yes, yes. Eric, are you ready for the next 4? Amber, not quite. Okay. Did you get these next 4? Amber, you ready for these? Yes. Julie, you ready for the next 4? Okay. Alan, you ready for these? Almost. Okay. All right, let's check. Were you able to get f of 1 equal to 4? Limit equal to 4 from the left. From the right, -2. And the limit does not exist. Yeah. I have 2 f of 1s, but this one's filled in, and this one is open. Well, it's not an assumption. It's by like a definition of how you label a point. If it's not filled in, that point is not included. If it is filled in, that point is included. Yeah. So this means when you plug in 1, this is the value that's included. When we do our limit, we get different ones whether we're coming from the left or the right. If you're coming from the left, you would be on this part of the graph, and you'd be getting closer to 4. If you were coming from the right of 1, you'd be on this graph, and you'd be getting closer to -2. And because you're approaching different values from the left and the right, the overall limit doesn't exist. All right, next 4. You ready? You're good? You're good? Good. Got answers for the next 4? You got the last 4? Okay. Good to go on the last 4? Yes? All right, let's see how it goes. F of 6 is 2, because that point is given to us. The limit, though, as you go from 6 from the left, right? We're coming from the left side, that's here. We get close to 5. From the right side, it gets close to 5. At 6, it exists this time, and it's equal to 5. Because from the left and the right, it's the same. But according to the definition of continuous, it is not continuous at 6. You have to lift your pencil up for a brief second and put it back down on the other side of that hole. Okay? So the definition of something being continuous, the limits are the same and the point has to be the same. If this point 6, 2 was filled in that circle, it would be continuous. But it's really easy to see from a graph where something is discontinuous. Here it's discontinuous, you have a hole. Here it's discontinuous, you got a big jump. And here it's discontinuous because we have another hole. So at the bottom here, in your textbook, page 27 and 28 has some questions. I've also given a handout from a bunch of different places with questions on limits. What's nice about the handout is you can bring the handout to other classes and work on it if they're not doing anything. If they're doing something, right? I get in trouble if I tell you to work on math in Mr. McWilliams' class. He gets mad, all right? We used to be able to do it more in English because there'd be final exams. So everybody be studying for their final math exam in English, and then he'd come and tell Mr. LaFrance and I that he's mad. That now it's biology and IB physics, right? So if you have time in another class, the worksheet is nice, right? If you brought your textbook to class here, the textbook is a nice one to work on here because you can work on that other worksheet in other places. Again, you have to decide how many questions you need to do before you feel like you're mastering the idea. Right, but it is the point on the graph. So by having this dot there, it's saying that 6 is part, yeah, it doesn't matter if it's on the line. You could have a graph with a bunch of dots.